Episode 3: Value Functions and the Bellman Equation. Imagine you're standing at a crossroads in a maze. One path leads toward treasure. The other spirals into dead ends. If only you had a number, a single number for each location, telling you exactly how good it is to be there. That's what a value function does. In this episode, we'll answer the question that Episode 2 left open. How much is a state worth? We'll define two functions, V of S and Q of SA, that assign a precise value to every state and every action. Then, we'll derive the Bellman equation, the recursive relationship that ties these values together and makes every RL algorithm possible. Let's ground ourselves in what we've built. In Episode 2, we defined the Markov decision process. 5 components: states, actions, transitions, rewards, and the discount factor gamma. We defined the return G sub t as the total discounted reward from time step t onward. And we introduced policies, mappings from states to actions that describe the agent's strategy. But we left a critical question unanswered. Given a policy, how do we measure how good it is to be in a particular state? How do we compare two states and say one is better than the other? That's where value functions come in. The state value function, V pi of S, answers a simple question. If I'm in state S and I follow policy pi from now on, what's my expected return? Formally, V pi of S equals the expected value of G sub t, given that the current state is S and the agent follows policy pi. It's the average of all possible future returns, weighted by their probabilities. Let's see this on our grid world. Under a random policy, where the agent picks each direction with equal probability, corner states near the goal have high values. The goal itself might have a value of 10. Adjacent states might be 7 or 8. States far from the goal have low values, maybe 2 or 3. And states near the trap, they could be negative. The value function paints a landscape over the entire state space. Peaks where good things tend to happen. Valleys where they don't. This landscape is the agent's map of the world. The state value function tells us how good a state is, but the agent doesn't just exist in states, it takes actions. We need a function that evaluates state-action pairs. The action value function, Q pi of SA, answers, if I'm in state S, take action A, and then follow policy pi for every step after. What's my expected return? Q is strictly more informative than V. If you know Q for all actions in a state, you can recover V by averaging over the policy. V pi of S equals the sum over all actions of pi of a given S times Q pi of SA. But the real power of Q is this. To improve a policy, you just look at the Q values and pick the action with the highest one. You don't need to know the transition dynamics. You don't need to simulate the future. The Q values already encode everything. Here's the key insight of this episode. Value functions have a recursive structure. The value of a state today depends on the value of the states you might visit tomorrow. Let's write it out. V pi of S equals the expected value of the immediate reward R plus gamma times V pi of S prime. In words, the value of where I am equals what I get right now, plus the discounted value of where I end up. This is the Bellman expectation equation for V, and it's one of the most important equations in all of reinforcement learning. It says that value functions are self-consistent. If you know the values of all the next states, you can compute the value of the current state. There's a corresponding equation for Q. Q pi of SAA equals the expected reward, plus gamma times the expected Q pi of S prime, A prime. where S prime comes from the transition function and A prime comes from the policy. Both equations say the same thing. Value now equals reward now plus discounted value later. Backup diagrams give us a visual language for the Bellman equation. They show exactly how value flows backward through time. Start with a state node at the top. Below it, draw action nodes for each possible action. Below each action, draw the next states that could result. This tree shows one step of look ahead. For V pi, the state node branches into actions weighted by the policy. Each action branches into next states weighted by transition probabilities. The value backs up from the leaves to the root. For Q pi, the action node branches into next states weighted by transitions. Each next state branches into next actions weighted by the policy. Again, value flows upward. These diagrams aren't just illustrations, they're computation graphs. Every RL algorithm we'll study, from dynamic programming to Monte Carlo to temporal difference learning, is really just a different way of performing these backups. So far, we've been talking about the value of states under a specific policy P. But what we really want is the best possible value, the value under the optimal policy. V star of S is the maximum V pi of S over all possible policies. It represents the highest expected return achievable from state S by any strategy. Similarly, Q star of SA is the maximum Q pi of SA over all policies. Here's a beautiful result. There always exists at least one optimal policy PI star that achieves V star simultaneously for every state. You don't have to trade off. Being optimal in one state doesn't require being suboptimal in another. And once you have Q star, the optimal policy is trivially simple. In each state, just pick the action with the highest Q star value. The hard part is finding Q star. That's what the rest of this course is about. The optimal value functions satisfy their own version of the Bellman equation. For V star, instead of averaging over actions using a policy, we take the maximum. V star of S equals the max over all actions of the expected reward plus gamma times V star of S prime. The optimal agent doesn't average, it always picks the best action. For Q star, the equation is Q star of SA equals the expected reward plus gamma times the max over all next actions of Q star of S prime, A prime. Compare these with the expectation versions. The only difference is that the policy average becomes a max. That single change, from expectation to maximization, is the entire difference between evaluating a policy and finding the optimal one. The Bellman optimality equations are nonlinear because of the max operator. This makes them harder to solve than the expectation versions, but they're the foundation of algorithms like value iteration and Q learning that we'll meet in future episodes. Let's compute some values on our 5x5 grid world. The goal is at position 4-4 with reward plus 10. The trap is at 2-3 with reward -5. Every step costs -1. Gamma is 0.95. Under the optimal policy, the agent always moves toward the goal by the shortest path. From position 4-3, one step from the goal, the reward for entering the goal is +10 minus the step cost of 1, giving us 9. From 4-2, 2 steps away. V star equals -1 plus 0.95 times 9, about 7.55. Now look at Q star values. In state 3-4, Q star for moving down is 9, because that takes us adjacent to the goal, but Q star for moving left is only about 6.2, because that adds an extra step. The optimal policy picks down. Notice how values decay as we move away from the goal. That's gamma at work. and near the trap, values dip sharply. The entire grid becomes a value landscape that guides the optimal path. Here's the deeper truth. Value functions are the currency of reinforcement learning. Every algorithm will study dynamic programming, Monte Carlo, temporal difference, policy gradient. They all revolve around estimating or improving value functions. The Bellman equation is the engine that makes this possible. It transforms the problem of computing values, which seems to require infinite look-ahead, into a local computation. The value of a state depends only on its immediate neighbors. Solve these local relationships simultaneously, and the global solution emerges. This is why we spent an entire episode on value functions and the Bellman equation. They're not just one topic among many. They're the foundation on which everything else is built. Let's lock in what we've built. First, V pi of S is the expected return from state S under policy pi. Q pi of SA extends this to state action pairs. Together, they measure how good it is to be somewhere and do something. Second, the Bellman equation relates a state's value to its successor's values. Value now equals reward now plus discounted value later. This recursive structure is the backbone of RL. Third, optimal value functions V star and Q star represent the best achievable performance. The Bellman optimality equation replaces the policy average with a max. In the next episode, we'll stop admiring the equations and start solving them. Dynamic programming gives us the first algorithms for computing value functions and finding optimal policies. Policy evaluation, policy iteration, and value iteration. The theory becomes code. See you there.